Okay, so I want to introduce Darko Marinov from University of Illinois Urbana-Champaign. He's going to talk about some automated testing tools to do automated test case generation.
Okay, thanks. Thank you, John. Thanks for the introduction. It's nice to be back at Google. I was here about 5 years ago. I guess it was somewhat smaller at the time. Haven't visited since then, but I'm back here. And I'll be talking about testing. I usually start with a few slides saying why testing is important, because that's unnecessary to say here. I know that everybody knows that testing is important. You have testing on toilets, so what can be more important than the space occupied in the toilet, right? So actually, what I'll start from is a motivating example. This from recent work done in collaboration with Google. And what we actually wanted to do was to test a program developed at Google. It's a joint work with Nemanja Petrovic. He's in the New York office. So what this particular program does is that as input, it takes some acyclic directed graphs. What these graphs actually do is they represent web. So they start from a web graph. So the nodes are actually sites, and then the edges in the graph are links. And it has some pre-processing step and reduces the strongly connected components. So eventually, what one ends up is having some directed acyclic graphs. And basically, what I'll be talking about in this talk is how to generate such inputs. And this is just an example of something that we call structurally complex inputs. What I mean by this is that the input itself is structural, so it consists of some nodes that are connected in some way. And by complex, I mean that these nodes need to satisfy certain complex properties. In this case, how these nodes are connected. Just here, for the sake of completeness, I mentioned what the output of this application is. But I don't exactly even know, because I never saw the application. We would just send here the tools for testing and get back the results. I never even ran any of that. I just know that it computes some kind of sets of nodes on certain paths. So it does some kind of traversal. So key point then is that the inputs for this application are some kind of complex data structures. And then the question is how to generate those. Here's some other examples of such structurally complex data. For example, library code often has a lot of such data structures, say something like red, black trees or other complex structures. If you look at the programming language, something like a Java code can be also viewed as structurally complex data. Now, if you just look at the text itself, it does not look like it has any structure. But if you build something like an inheritance graph, or we build an abstract syntax tree from this code, then we are going to end up with some structurally complex input. The same goes for something like an XML document, right? So if you have an XML document, if you parse that, build some kind of a tree, again, we end up with some number of nodes that are connected and need to satisfy certain properties in order to be a valid document. OK, so there is, I would argue, a lot of code that manipulates our structurally complex input. So here are some of the examples of such code. And what we would like to do is to test such code. For example, operations on abstract data types. If you look at something like library operations, say a set implemented as a red-black tree, then effectively each operation that, say, removes or inserts an element into the set actually takes as an input a data structure that needs to satisfy appropriate invariants for this data structure. If you look at some code that processes, say, Java programs, for example, an integrated development environment like Eclipse or NetBeans, the input effectively there is interesting Java programs. They may be legal or illegal. Maybe we want to satisfy the syntactic and semantic requirements, maybe intentionally not, in order to test certain parts of the IDE. We can look at XML processing programs. Again, they take as input XML documents, and so on. Basically, in all these examples, we have that the inputs are structurally complex. And here's then the general setup of this testing, how one may want to test that code, and certain assumptions behind our work. So we will first start with some test input generation. So the goal there is to produce a number of inputs. Remember, each of these inputs is the structurally complex thing. We'll give one by one to the code under test. This will produce a certain output. Maybe we are just giving an XML document, and then this code processes and outputs another XML document. Maybe we are just giving some red-black tree, and we are inserting some element or removing, and then as an output, we effectively obtain another tree, and so on. And then we take each of these input and output pair, and in some way, we check whether this passes or fails, whether the code was correct for this input or not. So I'm not going to talk about the testing oracle at all here. I'll just focus on test input generation. And some assumption that I make in this work is that the first basic one is the tester has some good intuition about these inputs. I guess probably the zeroth assumption is the tester really cares about doing this testing and cares to produce good inputs. That's usually the case. And I also use tester in the broad sense to mean the person who is doing testing. I know that here you have a lot of developer testing going on. It's actually people who have the title of developer who are actually doing the testing. But basically, the person who wants to test the code, the person who is coming up with these inputs. So the idea is that there is good intuition there, and the person knows what are the properties of these desired inputs. You know, if it's XML documents, you know what kind of documents you may want to generate. You have some kind of intuition what may expose a bug. You know, what kind of, where the bugs may be in the code, which parts of the code may be more buggy than the others. However, the problem is that even though you know the properties of these desired inputs, there is a large number of them. If you just look at our example with DAGs, the Google application that was processing DAGs, there are just many corner cases for that. You know, you will need to test your code with an empty graph, maybe something that looks like a list, something that looks like a tree. Then you want to have some kind of sharing where there are multiple incoming nodes. You need a graph with multiple routes, disconnecting components, and so on. So even though it would be fairly easy, relatively easy to state the properties of this and just say the inputs to my code are directed acyclic graphs, it's quite hard to go and manually actually enumerate one by one of these graphs. So if you look then at this, the comparison of manual and automated testing, the manual is just tedious and error prone. You know, you need to start from some cases and just generate, you know, an empty graph or some small graphs, and you need to go to larger graphs and so on until you either run out of patience or just, you know, run out of the space on the slide. And then you just say that you're, you know, exhausted with your testing and you stop there. Also, if you go and change something in the code, if you need to change these inputs, you will need to go and manually, you know, change all these inputs. So I'm not saying that you shouldn't do any of this. Clearly, you should do that. I mean, people do write manual tests. You should write some of them. But what I would like to do is to help testers when they actually want to generate a large number of tests. And here's then the solution that we propose for doing that. The idea is that instead of manually writing these individual tests, tester manually writes something that I call test abstractions. So the idea is that each of these test abstractions actually describes a set of inputs. I'll show more examples of these test abstractions as we go. So we just describe here that, you know, I want to generate graphs that are directed and acyclic graphs. And then the tester does this manually, and then the tool will automatically generate specific concrete inputs. So the good thing here is not only that the tool can generate a large number of them, you know, thousands, millions, or billions of them, but also that if there is some change that's necessary, maybe you want your inputs to be represented a different way, maybe you want to test a different part of the application where the input should be slightly different, you only need to change this test abstraction. The tool will automatically regenerate inputs. You don't need to deal with individual inputs. Here's some sort of a summary of some results that we've done for these test abstractions. We've actually developed two kinds of test abstractions. One is based on declarative. So the idea of declarative is that the tester simply describes what the inputs look like. So in our case, the example with DAGs, you would simply say that you want graphs that do not have cycles in them. The other approach for test abstraction is imperative, whereas instead of saying what the inputs look like, the tester would describe how to generate these inputs. And I will touch a bit on both of them. If you go now back to this declarative example, so there the tester should write what the inputs look like. There's still the question of what language to use to actually describe these properties. Right, so if I just tell the machine, you know, I want the graphs that are directed and acyclic, it's not going to understand that. You work a lot with natural language processing, so you know that machines are not there to understand that. So we would need to express this in some other language. And actually, there I worked on two approaches. One is to use the actually declarative language for properties of desired inputs, and this was relatively good. So we get, you know, publications out of there, because that's something that counts in academia. Unfortunately, we don't get users. It turned out when we use this language, when we use this approach, that we couldn't get many people to use this. The issue was that we use some, you know, languages that are just developed in academia and mostly used in academia, something called Alloy, and there is some learning curve there, maybe relatively steep learning curve. And we just couldn't get people to use that. So then we switched to doing something else. and to using the actual programming languages, such as Java or C#, to describe these properties of desired test inputs. And this turned out to work much better. This is something that has been used in industry, at Microsoft, and even now at Google. And this is something that I'll be talking more about. Specifically, I'll be talking about an approach that we call Kirat there. It stands for a saw. That's where this comes from. And also, I'll touch briefly on this AST-Gen, which is a more recent work. So before I go to describe the details of what these tools do, I would just like to say, to mention one common use case for this tool. It's something that we call bounded exhaustive generation. So the idea there is that you want to generate all of these test inputs up to a given bound. It's not necessary. You don't necessarily need to do that. You can always sample in one way or the other a number of inputs. You may do that randomly or in some more informed way. You may sample, but nowadays that the machines are quite powerful, there is no reason to not try all of them, at least for small bounds. So the idea then is that the user will not only give this test abstraction, not only how the inputs look like, but we also provide the bounds. So in our case with the graphs, the user will say how many nodes there are, maybe what are the possible values for these nodes, and so on. And the reason why you may want to try this testing with all inputs up to a given bound is that clearly it can find the bugs that can be found within that bound. So this can cover many corner cases without explicitly thinking about them. And the setup then looks like this, that the user has to provide test abstraction in the bound, and the tool will then generate all structures, or almost all structures within that bound. Okay, so here's the outline of the rest of my talk. After this overview, I'll present one of these tools called Kirat, present an example of what it does, then give some brief demo of how to use it. Hopefully the demo will work. And then I'll just briefly discuss how it works. I won't go much into those details. I'll spend more time on the results of where it was used and how it was used and what kind of bugs it found. Then I'll briefly mention this AST-Gen, which is more recent work, and conclude. If you have any questions, please feel free to stop me at any time and ask. OK, let's see then the example. So as I said, there was this application we wanted to test that was developed at Google. And as inputs, effectively, it takes directed acyclic graphs. Now, in order to use any of these tools that we developed, the user has to first describe how these inputs look like. Kirat tool was implemented for Java. So one way to describe that would be, for example, to write these classes here. The user can write some class DAG, which represents the graphs. They have some list of all the nodes in there and some certain size. And then these graphs consist of a number of nodes. And each node has a number of outgoing edges called here children. So this is one part that you clearly have to do. You have to describe how the inputs look like. Also, the user has to express the properties of objects of these classes. The fact that we called something DAG does not mean that we cannot create a cycle there. You can just put two nodes that point to each other. So the user has to describe to the tool these properties, that there should be no directed cycle among the nodes, and that all outgoing edges from a given edge should be different. As I said, we worked on a number of languages and approaches for how to do that. The one that I'll describe is something that we call Kirat. And the idea here is to describe these properties as imperative predicates. An imperative predicate is basically a piece of code, say written in a Java, that identifies these desired structures. So the user will have to write a piece of code. I'll show that on the next slide. And this will take an input that's either a DAG or a not. So this code takes as input an object of a class DAG. But then it needs to check whether these objects that are reachable from the node actually satisfy these properties or not. Then it will simply return true or false to indicate whether this is an input that's desirable or not. As already said, we've tried some other approaches that are good for publishing papers and doing research. But unfortunately, it will take some time for something like that to take off in the industry. And using actual languages for expressing this property has a number of advantages. First, the language is familiar, so people know how to express these properties. Then there are existing development tools. So there are development environments that people can use to actually write these properties to debug, to see what's going on. And also these predicates that describe the structures can be already present in the code. Here's an example of how this can look for the DAG. I'm not going to go into all the details, but I wanted to show the entire example, first to show that this is not too hard to use. Another way to argue that it's not too hard is to say that we usually have undergrads who go and write things like this. So we just ask the undergrad students effectively to write a piece of Java code that will check whether certain graphs satisfy properties or not. In this case, remember, we are writing DAGs. So what we want is that the nodes reachable from the root actually do not have any of the cycles, do not have a directed cycles, and also that the edges that go from one node are different. So what this particular code does is just some standard textbook traversal of the graph. I believe it does breadth first or depth first. I don't even know the exact details. As I said, usually undergrads, we just ask the undergrads to go and write things like this. The point is that this is not too hard to do. So effectively in this 20 lines of the code, one can go and encode this property. So instead of generating individually one by one of the graphs, what you need to do is just write this, and then the tool will generate a large number of the graphs for you. OK, but before the tool does that, it also requires another piece of input, which is something that we call finiteization. And the idea here is that the user needs to bound the size of the structures. So if you want to generate these DAGs, the user needs to say how big these DAGs should be. For example, we may want to say that we want to generate DAGs that are of the size exactly 3. So we want to have exactly 3 nodes there. So what that means is that the user has to specify that there is one DAG object in one graph, in one given graph. We'll be generating a large number of them. Then there are 3 node objects. And then also to specify the values for these fields. For example, for the size, we may want to have the value exactly 3. In general, we want to put values 0 to 3 or 0 to n. We don't want only of a specific size, but maybe all of them up to some given size. And then it needs to specify the values for these outgoing edges. So we had some array called children in the DAG node. So there it's necessary to specify what are the possible length for that. Effectively, what's the number of outgoing edges. OK, so now if the user provides that, if the user writes this imperative predicate, basically this piece of code that checks the properties, and also writes this finiteization that describes the bounds on the inputs, then this tool, which we call Kirat, can generate almost all structures within these given bounds. And then you can use them all effectively to test your program. The way that this internally works is that Kirat searches this input space to find appropriate structures. And I'll mention just briefly how it actually works inside in a few slides. But actually, what I would like to focus on, instead of just describing how it works inside, I'd like to give a bit of a demo of how one can use that and what exactly it does. So the tool itself is available from SourceForge, so it's in open source, mostly developed by 2 undergrads, Alexander Milicevic and Sasha Misilovic. It's fairly hard to get grad students to spend a lot of time to develop something that goes in open source, especially if they're close to graduating. But undergrads can get these things done. So the tool itself is implemented in Java, and it works on Java predicates. So I'll mention later in the talk, the same idea has been used at Microsoft. Of course, they work with C# and the other languages. And this particular tool is just a command line tool. So basically, it takes a number of parameters. You need to say for which class you want to generate these structures that are to be used as test inputs. What is the predicate that describes the properties of the structures, and then provides these bounds. And then what the tool can do is either visualize these structures or save them in a file for later reuse or run the code under test and so on. Here's an example of how that looks like. So if you were to type something like that for running the tool, you say that you want to generate these DAGs of the size exactly 3, and you want to visualize them. The tool will effectively produce something like this as the output. And here's then the demo. I will actually demo the tool. I will run this in Eclipse. So what I'll do in this demo, I'll show some example predicate and finiteization. And then I'll show how the tool visualizes this. So we didn't build any of this visualization. We just used an existing module developed for the Alloy language. And this visualization often can help in correcting the predicate if you just get it wrong. And then I'll also point to two issues, this generation of equivalent structures and the total number of generated structures. Namely, one, using this approach, one can end up with a large number of structures. So then the question is what to do about that. OK, let me proceed to demo. Before I do that, let me ask any questions. OK. Yes, actually, we have a question.
So the searching algorithm produces lots of structures and then tests whether they're OK or not. So what if the search space is much larger than the actual space you want? OK, so that's a very good question. The question actually is, I guess, at some level, how does this work internally, right? Because if you look at all the graphs, here's the answer, was on the next slide. But I'll come back to the demo after I answer this. So the question was, there can be a large number of graphs, and we want only those that are DAGs. How does the tool actually work? And this is actually the key challenge in building this tool, how to efficiently generate these inputs. Right? So if our goal is to identify only those graphs that are actually directed and acyclic, well, one thing we could do is, well, simply go and generate all possible graphs within this size, and then for each one of them, check whether it's a DAG or not, and therefore only output those and say these should be used as test inputs. But the problem is exactly as you said, this is something that we call a sparse input space, that the number of those that are desired can be much smaller than the total number of inputs. And then this brute force search, where you would try to enumerate all of them, is just not going to work. So what this means is that one has to be much more clever than that. So I'm not going to talk much about that. I can just mention here one slide summary of that. I have a whole talk that's just dedicated to that. Basically, what it does is, I mean, the idea is relatively simple. So what it does is it still starts the enumeration as if it's going to generate them all. And eventually, it is going to systematically explore everything. But what it does is the pruning. That's the key thing, is if it tries this predicate on one structure and finds that it does not satisfy these properties. For example, if it tries one graph and finds that it has a certain cycle in that graph, what it does then, it can prune a large part of the search space by effectively saying anything that sort of has this as a subgraph will also have this cycle and will not satisfy these properties. So that's the key idea, that you generate one structure, you execute this code on that structure, but while the code is executing, the tool monitors what's happening during that execution. How is this code inspecting this structure? And basically it tries to learn from there what the properties are, and then uses that information to actually find that a large number of similar structures should not be even explored because this piece of code is still going to return false. As I said, this is just one slide summary, but there are much longer descriptions in the paper. Yes?
To create a set of test inputs which were all directed graphs with 2 cycles each, then this approach would not exactly work.
OK, so the question is, what if you want to generate graphs that have 2 cycles each? For example. Yes. Yes, so you said the approach would not work. I guess the approach would still work in a sense it would generate them. The question would be how efficient it is, right? Or how effective it is. If you want to generate only 2, you would need to extend the description, right? So instead of having just this, you would need to add more code that maybe checks here, that check the number of cycles and see how many of them there are. If you add that at the very end, then the tool won't be able to prune anything, because if you're just counting that at the end, once you generate this DAG and you count the number, if it sees that there are 2 or 3 or 4, there is not much that it can learn from that. However, you can be counting the number of cycles as you go. And then you can say, if I see more than 2, I don't want any more. So what I want to say by this is there is some intelligence that the user, the tester, needs to put into writing these predicates. You cannot just directly write maybe the first thing that comes to your mind. You need a bit to think and to understand how the tool works in order to write the predicates that would make the tool work most efficiently. It's not always the case. Sometimes you can just write the very first thing that comes to you naturally, and that will work fine. Sometimes you need to tweak and tune these to get better performance from the tool. But in some sense, it will work. It will generate everything. It may just search too much in order to find the right things. OK, any more questions on things that I didn't want to talk about, how the tool works? OK, if there are no more questions, let me then show how the tool actually works. So here I'm just showing the Eclipse development environment. What do you use here? What do people use for writing? Eclipse and IntelliJ? OK, well, we don't use IntelliJ at school because it costs money. So use Eclipse and NetBeans. OK, so here's the Eclipse. And here's the code that I showed before. There is a class DAG on the left. And so it has this list of nodes and the size. And then there is this, the repk method. There is this piece of code that I wrote to check the property. Here I'm checking for that whether it's a graph or not. And here's the class for the node. And it also does its own traversal, however that it does. So here I've intentionally put an example where there is a problem. So I'm actually going to generate multi-graphs. So I'm going to generate things that I don't actually want to generate. Suppose that I'm not aware of this, of course, just for the sake of the demo. I go run the tool. OK. Hopefully. OK, so the tool is running. So one part of output that it gives is just down here. Basically, it says how big was the search. So it tried 21 structures and found 14 of them to satisfy the property. And just says how much time it took there. So that's part here. And then it also shows this visualization where it shows the graphs that were generated. So suppose now that our goal was to generate DAGs, and we wanted to have only one outgoing edge from each node. Now from this here visualization, we would see that we actually wrote an incorrect piece of code. We didn't specify the properties correctly, and so we have these two outgoing edges here. All right, so what we will do then is go, and change this piece of code. Of course, I've done that in advance. So I've prepared the one. And here I'm executing actually another one that corrected that problem, such that we are actually checking that there are no outgoing edges, that all the outgoing edges from any given node are different. So in this case, we run this again. And now we are getting these graphs here. It turns out we are getting 8 of them. And we can go and see them one by one, how they look like. And now, of course, the careful viewer could have noticed that some of them are the same. Anyone notice which ones are the same? Actually, this one, and effectively this one, they just look the same, except that they are flipped around, right? And the thing is that you may not want to waste your resources and to test with both of these, right? So it may be very well that they are just equivalent inputs, and they're either both going to find bugs or none of them is going to find a bug. So you wouldn't want to run them both. So there are some ways to tell this tool to actually eliminate some of them. And I've also prepared that this thing here, which is called reduced. Effectively, what I'm doing here, every time I choose to run one of these configurations, I'm actually running a different method here. So there are these methods called repk, correct, and reduced, and so on. These are different ones that are slightly different and do different things. So you as the user, so you as the user would need to actually write this to obtain different results. So now if I rerun this, so now instead of 8, I'm actually getting 7 of these structures. And as it turns out, I don't have that equivalent one. All right. So there is no need to go through all of them. So that's basically what the output is. Now, of course, I don't need to run this only for 3, right? I can go to larger sizes. So if I run for 4, this is still sort of acceptable. It finishes less than a second. If you run for size 5, now this is almost coming to the second. But we see that the number of these structures is growing. So now here we are getting about 5,000 of them. So clearly, when we go to larger bounds, this is going to grow exponentially. So we'll soon, the size is 6, 7, 8. We're going to hit millions of them. And probably we wouldn't want to go anywhere beyond that bound. So it's not that this testing will solve all the problems. It's not that this tool will go through all the cases. But it will definitely help with all the corner cases within small bounds. And I will also argue that there are a lot of bugs that are actually there. That if you try something like this, you may find a large number of bugs for which you don't even need the larger inputs. Of course, this doesn't mean that you shouldn't try any larger inputs. If you want to do any kind of performance testing, you need larger inputs. Even if you want to do correctness testing, you need larger inputs to cover certain cases. Okay, this was basically then the summary of this demo. So I showed the bits and pieces of this code, how it looks like, and what the tool does, and how it visualizes these things. And there was this part, which I want to skip over, which is how to use the tool, how the tool works rather internally. And I want now to show how how this tool has been used in actual scenarios. Any questions before I go to this? OK. So here's an example testing scenario, something where this idea was actually used at Microsoft, not the Kirat tool itself. As I said, there is a different implementation there for different languages. But the goal there was to test a program that processes XML documents. In particular, this was some expat compiler, if you know what that expat is. If not, some sense it's irrelevant. The point was that they had two implementations for the same thing. So they had the base code, which was a slower version of the code that was doing the same thing as the optimized code. And then effectively, the goal was to test this. So in order to test these XML processing programs, you need to give them some kind of XML input. So a way to use this Kirat tool, to use the idea in there, is as follows. You would first create some kind of a model for these test inputs. In this case, for XML documents, you don't want to generate them at the character level. Rather, you want to generate the syntax trees. Then you would write the predicates that specify which of these inputs are valid. So how do you want these elements in the XML document to look like, maybe what depth of nesting you want to have, and so on. Then you would use the Kirat tool to generate these valid inputs, translate them into the actual inputs, and then just run them through the both of these versions of the code, and then compare whether they are getting the same output or not. So this is just one possible testing scenario for using this tool. Something similar was also done here at Google. There was optimized code written in C++ that was doing this web traversal. And then they wrote this base code, which was a very naive implementation and the slow algorithm just written in Java, and then just compared the outputs from the two. All right, so here are then some of the results of using these tools and using these approaches. We've used this at school. We've done some kind of thorough evaluation of textbook data structures. That's definitely not all that interesting for industry, but something that should be done for the papers. And basically, the results show that this tool was useful. More importantly, this tool we've also used these tools to find errors in some real applications. Here's a list of some of them. There was some work also done by some other people initially on testing something called fault tree analyzers. Basically, these are the programs that take as input something called a fault tree. This fault tree describes how a system can fail based on how the subsystems can fail. Details don't matter, but the point is that the input is, again, structurally complex data, something for which these tools are very well suited. And then they've used the tools to actually do this checking with those declarative predicates. Point here is just to show some of these numbers that you can generate millions of these tests. And then it can take hours or days to actually generate that and execute. Another point also is to show that the tools are useful. For example, there were 20 bugs that were found in those things. OK, so even more importantly, the Kirat idea has been used at Microsoft. So initially at Microsoft Research, the Foundation of Software Engineering group there has implemented the Kirat algorithm in a tool called ASMLT. That's what they did initially. And so what this tool does is it works with the language called abstract state machine language. So rather than using Java or C#, one just uses this ASML. And they've engineered the tool very well. So there's some GUI for setting all these finitization, manipulating tests, re-executing that, and so on. The Kirat part can be either used standalone to generate these test inputs, or very often you're not interested in just generating these graphs or any kind of inputs by themselves, but maybe they're just part of a longer sequence. So you can also use that there. And then there are a number of extensions that were also built. So when one goes to actually build this tool and use, then there are some extensions that needs to be done compared to our academic use and building these algorithms initially. So some of these extensions involve this controlled non-exhaustive generation. So if you don't want to generate all of the inputs within a given bound, but only some of them, then generating complete tests from partial tests and so on, building a library that understands actually many of the common data structures and works with them. There was also summer intern there, 4 or 5 years ago, and actually worked on some of these things. And the tool has been used there. It was initially built in research, but then moved to production. It was used by testers in several product groups and enabled these testers to find numerous errors. Again, I would like to point out that this tool is not magical. It's not just going to look at your code and find the errors. You have actually to put some effort into using the tool. You need to describe the inputs. You need to write the predicates and so on. The most important thing is you need to have some good feel for where the bugs may be and what kind of inputs to generate. But the thing is that the tools still help people to actually find these bugs. So they've used that, for example, for XML tools, specifically for that XPath compiler. I've shown that graphical view of how they use that. And there they found some 10 coding errors. And as it turns out, this was a piece of code that was about to be released. So they've already had a very extensive test suite built manually. So in this case, they used the tool to just augment that test suite. And as I said, just found a number of coding errors that they did not expect to be there because they've already done the best job they could manually, and even doing some random things with randomly generating XML documents and so on. The problem with random generation is that you don't have much of control of what to generate and where, whereas using tools like this, you can have a more focused generation. They also tested something called serialization. They found 3 code errors, but this wasn't all that interesting because this code was nowhere near release. It was just at the initial stages. What was interesting there is that the spec was changing. They would keep changing the spec and what this code should do and how. And there they found that using this tool was really helpful because as the spec changes, as the code changes, they could much easier change the inputs if they just go and change that predicate. So if they had thousands of the inputs manually written, whenever they need to change their format or how they look like or what properties they satisfy, they would need to do that manually. It would be quite involved. With the tool, they need to make much smaller changes, and the tool would just regenerate everything. They also found a number of issues in these web service protocols and many others. I don't even know what are all the other things for which the tool was used. Just a few years back, when I need to talk about this, I asked for permission for talking, and I was allowed to talk about this much. So the point was that the errors were found in important applications that they already well tested. And here are some comments that we received from Microsoft, from the actual people there in the trenches, from the actual testers who use this tool. So we got some positive and the negative comments. I want to point out that negative comments are not on Kirat. I'll come to that. So the positive comments are on the tool itself, because that's what they're using. And then I like to point out that these positive comments are also on the Kirat. So Kirat is my idea, so the positive thing is about my idea. So one of them says, so far our stateless SML models are pretty successful. But remember, the tool that they're using is called SMLT. So basically, the way I want you to read this is, so far Kirat is pretty successful. So the thing that I did is pretty successful. SML parameter generation tool is quite convenient and powerful, as you can guess. The way I want you to read that is this, that the Kirat algorithm is quite convenient and powerful, and it was just implemented in this tool. So these were the positive comments. But then, as I said, we got some negative comments. What I like to point out here is that they are just on the tool. They are not on the algorithm. Okay, positive stuff is about my algorithm. Negative stuff is not about the algorithm. So what these negative comments basically said was, most of our testers prefer to write as much C# as possible. and things very difficult to debug ASML. The issue here was that the tool was initially built ASMLT around this language ASML because that's what they had in the group. They already had the tool. They just added this as the extension. So it was a quite natural choice to do. But it's not something that people like because it's a new language and they have to learn that and so on. So as a result, then the group has reimplemented a new tool for C# and actually all .NET languages. And the tool is called Spec Explorer. And it's also available online in some kind of agreement from them. Definitely available for academics. All right, this was about the use of Kirat at Microsoft. We've also used this at Google. As I said, this was done in collaboration with Nemanja from your New York office. The goal there was to test some web traversal code. I said there the test inputs were based on DAGs. And also, as I mentioned, I don't even know what the code does. I never saw that code. But the key thing was that we could use Kirat for that. The issue, however, was that we would get a very large number of inputs. So if you just go to generate all graphs of the size 7 or 8, you already end up with millions of them. And what we wanted to do was to make this generation and execution faster. And of course, the first idea one would want to try would be to parallelize this. But there's a big challenge there that the Kirat search is mostly sequential, again, because I didn't present the search. I cannot argue why it's sequential, so you have to trust me that it's that way. So that was a challenge, but we came up with some solution and developed actually a family of algorithms that can parallelize this execution and generation. And here are some of the results. So this is for these graphs of size 8 for one of the algorithms that we developed. These experiments were done on your computing infrastructure. So here's the speed up shown as the number of machines increased from 1 to 1,000. The testing time itself dropped almost linearly. So it went down to over 500 times. So it reduced from some 36 hours to about 4 minutes on 1,000 machines. So I guess it comes down from some weekend break to the coffee break that you can run this. This is mostly for execution. And again, one could even ask, maybe I can just at least a bit mention what the challenge here is. Well, if I just have this way to generate these test inputs, why don't I just save them on disk and then later on go and re-execute them? And of course, I'm going to get a curve like this, right? I'm just going to distribute that for generation and do this. But the problem with doing that is that if you have too many of these inputs, then it's going to take a lot of time to distribute that. And so you don't necessarily want to do that. So this actually includes the generation time as well as execution time. Here are some more experiments. This is for some DAGs of size 7. And here, actually, the curve does not look all that good because it reaches some peak on 128 machines, and then it starts going down. And here's actually the issue where it's visible that a lot of time goes on this file distribution. So we use this Google file system and whatever that it exactly does and however that it works. So that was one part of this doing parallelization and making this thing to work faster. Another thing was to reduce the number of test inputs that get generated. So as I said, there is a way to do that by slightly rewriting those predicates that get written. One can eliminate some equivalent inputs. Again, I'm not going to describe the details of that or how it works, but here's some summary of the result. Basically, by investing some more effort, this roughly measures the effort that the tester has to invest in using the tool. By investing some more effort, you can obtain impressive speed ups in the execution and the generation time. So here, the number of inputs dropped significantly from 1 million to 20,000. And then here's the generation time that went down about 7 times.
Can you say what your equivalence classes are?
OK, so equivalent, I guess in general, equivalent classes would be those that, if you have a set of inputs in one class, either all of those inputs show a bug or none of them shows a bug. So clearly, we don't know that unless we run them all and see whether they show bug or not. So there is this part where it says here, deemed equivalent. So it's whatever that the user believes to be equivalent. So if you're testing this code, you may want to say, well, I think that there is no need to test with all graphs of size 3. I'm going to choose literally only one graph of size 3. And then you would just say all inputs that have size 3 are equivalent. Or you could say, well, all inputs that look like a tree are equivalent. If I have some bug, it's enough to test on only one tree. I don't need all the other trees. Probably I have some bug when there is cycles and sharing. Don't waste time with the trees. So basically, it's completely up to the user, whatever the user finds to be equivalent. So the tool has some built-in equivalence. It can deal with some isomorphic structures. It can remove those. But the user can manually add some more things and then remove even more. Okay, so basically this finishes then the talk about the Kirat tool. So in summary, what it does is it requires the user to describe what these inputs look like, and then to provide the bounds on the size of the inputs, and then the tool will just go and automatically generate all those inputs. Any questions about that part? Yes?
Can you please just clarify a little bit more how pruning works? Do you
Let's
actually
say that-
call the validity predicates for each thing, or do you sometimes avoid calling them based on previous results? I did not understand that.
Okay. So the question is how the pruning works. Let's try to keep that for offline. I need to finish in like 8 minutes, and I have a few more slides that I would like to address, and then we can discuss that after. I mean, yeah, I would. Yeah, no problem. I would definitely like to talk about that. By just if I talked about that, I wouldn't have time to talk about anything else. So. Okay, so the question about pruning, we'll discuss that after that. Okay, so the point then is that, yes, there is this pruning that goes on. Effectively, you just tell what to generate, and then the tool somehow needs to be smart about that and to do the search in a smart way to actually generate that. And now what this other tool does, this tool called ASTgen, is different. So rather than describing what the inputs look like, the user or the tester has to specify how to generate these inputs. So rather than writing the code that checks properties, you have to write the code that directly generates these test inputs. So the trade-off here is that this usually results in faster generation because there is no this search going on. There is no pruning. You can directly generate this. But it's often more involved to write these generators. So what we've actually done is built a large library of some of those generators, and provide this library, provide this framework that has a number of them built in. And then if you want to use that for a specific purpose, one has to extend that. So if you want to generate certain kind of test inputs, you need to extend that in a specific way. So the library just provides some generic basic inputs. So the first extension that we worked on was for generating abstract syntax trees of Java programs. And ASTgen actually is a name of a larger library. There is an underlying library that can just generate the basic things like your list trees, graphs, and things like that. So what we did was here for the abstract syntax tree, the goal was to actually test some parts of Eclipse and NetBeans. Particularly, we want to test something called refactoring engines. If you know what that does, it's great. If not, the details don't matter. The point is that they take as the input, they take effectively Java programs. So the question then is how to generate those Java programs. And if you're testing this, you may have certain intuition about where the bugs may be. So here's one of those examples. You may be able to succinctly express in a natural language what kind of inputs you want. Maybe you want to generate a Java program that has a pair of classes. It has two classes that are related in funky ways. Maybe one is inner class of the other, or one inherits from the other, or maybe it's both inner and inherits, and so on. And you want one class to declare a field and the other to reference the field in some way. So we can write this in English fairly easily. The problem then is if you want to actually generate programs that satisfy this property, then there are like thousands of them, or millions, just depends on what bound you put. There is actually unbounded number of them. So the question again is, how can we help people to turn this intuition into effective test generation? And as I said, this ASTgen helps with that, but you need to invest some work and to actually write pieces of code that will generate appropriate abstract syntax trees. And some of the results, we've used this tool actually to test this in Eclipse and NetBeans, and we've reported 47 bugs, which we believe to be new and unique. And they've confirmed 20 of them in Eclipse. And then in NetBeans, they've confirmed a number of them, fixed some of them, but then they've labeled some of them as duplicates, although we still think that they're not duplicates. It's a completely different question what testers think versus what developers think. OK, so that was about these tools, just briefly. STGen. Here's a list of people that I worked with. These projects and this line of work on test abstraction has been going on for 7 or so years. So clearly, I wasn't the only one working. So on the left are people that I worked with more recently. Some of them at Google. I said Nemanja is a full-time at New York. And then Alexander Milicic was an intern this summer. And then on the right are people who were involved in somewhat older work, the initial work along these lines. And the person in common is Sarfraz Khurshid. It just turns out that the name came also there in the alphabetic order. So the two of us have been collaborating on this actually for years. OK, so this is basically about this approach. So the idea was to use these test abstractions. So rather than manually generating a number of test input, just describe how they look like. And then the tool will automatically generate. There are a number of other related testing approaches doing that. So there's something called model-based testing. We can view this way of test abstraction as a special case of that, where our models are actually these predicates. There's something called specification-based testing. Again, the idea is pretty much the same. You write some specification for how test input should look like, or what is it your code accepts, and then generate test inputs from there. Maybe a bit of a difference in our work is that we focused on this bounded exhaustive generation rather than just random. There's constraint-based generation, again, fairly similar to that. Then there is random generation, something that people do use, but it does not provide the same guarantees as bounded exhaustive. It also makes it hard to generate inputs when you have these sparse spaces. There's grammar-based generation that's used if you want to generate programs, XML documents, things like that. But again, if you want very complex properties, it's hard to express that in grammars, and so on. OK, so here then to conclude, well, testing is important, as we know, and as you know, and I guess as you practice it. What I talked about in this work was something called structurally complex data. So it's something that's increasingly used in modern systems and poses some important challenges. It's just not obvious how to generate that automatically. And I've presented some tools that help with that for automated testing of structurally complex inputs. So one tool is this Kirat. Again, it's available online, provides some efficient bounded exhaustive generation. Said it was effective for data structures in our evaluation, also adopted in industry, used at Microsoft, found a number of bugs in actual code. And this more recent tool called STGen, this does some imperative generation, somewhat different, and we use it to find a large number of bugs in these IDEs. So I would definitely encourage you to try out these tools and let us know what you think. You should have some sort of manual on these web pages. And it would be great if you get to try that and give us some feedback. OK, that finishes my talk. Question? Yes?
And please make sure you repeat it, just
OK.
so I don't have to get up. But anyway, can you say something about oracle generation? Because
OK.
The relationship between the input and the output with automatically generated data.
OK, yes. So the question is if I can say something about oracles. Well, there's not much I can say. I mean, clearly, you can build one oracle this way, but this is going to involve some work, right? So if this is the actual code you want to test, you can go and implement another version of that, and then just go and do comparison. Another thing that can be done is just to have some partial oracles. So simply, you would run the input, obtain the output, and in just some way try to, see whether is this output incorrect or not, even though you don't have the full check, as in here. So the simplest case, if your application crashes, then presume there is something wrong with the application for that input. Another thing that we've done, for example, in checking these refactoring engines in IDEs. So what refactoring engine does, I can explain that in a sentence. It takes a program, let's say a Java program, and then just changes it. Basically, it just translates from source code to source code. So now if you give it a program that compiles and it produces something that does not compile, that's definitely a bug in the refactoring engine. even though you don't know what the correct output program should be and what it does, if it produces something that does not compile, that's a bug. So then this is a very partial oracle that just checks for some kind of sanity property on that. Sorry?
Is that what you did in that?
Oh, no. For this, for the actual STGen, we built a large number of oracles for that. I mean, the basic one that we used is this differential comparison between two things. So we would give the same program, run it both through NetBeans and Eclipse, and then compare, are they getting the same output? But even if they get the same output, they may be both getting the same incorrect output. So then we would still need to run some additional things to make checks. Actually, we found things where both of them have the bug on the same output, right? So you couldn't detect that if you just compare the outputs. Okay, any more questions? Well, I guess the pruning is a pending question, but take me some time to explain what that does and how.
All right, thanks a lot.
Okay, thank you.